All right. Today we're going to talk about improper integrals. So this is the intro to this section, 6.8 in your textbook, which is Apex Calculus. You can find that PDF on Canvas. There's also some other resources on there, including other videos and other online texts that cover the same topic. So you can check those out if this isn't all making sense. And then on Monday and Wednesday, we'll meet at our regular class time on Zoom, and I'll send out that meeting ID, and we can ask questions about it. There's also a quiz that goes along with this that's available on Canvas as well in the module. So we're going to make modules for each one of these sections. Okay, so what is an improper integral? So there's improper integrals are kind of definite integrals. So what we're talking about is area under a curve. And with an improper integral, one of the bounds is going to be infinite. One or both of the bounds will be infinite. So, for example, we might, want to take an improper integral that looks something like this. So 0 to infinity, and let's just pick a function that's easy to graph so that, we can get an idea of what we're doing. And so here's a line, x plus 2. It's got a slope of 1 and a y-intercept of 2. So let's draw this. So y equals x plus 2. 2 somewhere over here. And then it's it's a slope of 1, so it's just sort of cutting through here. So here's y equals x plus 2. And then let's think about what this is saying. So the bounds for an integral are an x value. So we're starting at 0 on the x-axis, but we're going off to infinity, whatever that means. And so we're just letting this continue on and on the right hand side of the. And so for this kind of function, notice that as we go further and further, the area that we're trying to talk about is just getting larger and larger and larger. And so we might guess, and we'll see when we define this in terms of limits, that this is the case, that the area between 0 and infinity of x plus 2 is going to be infinite. And what we're more interested in these, when we're studying improper integrals, are what are some functions whose improper integrals don't give us infinity, because you would guess most of them would. So how would it work if a function was such that I take an integral from some finite value to infinity, but the area under the curve is somehow not infinite? So what would that look like? Well, one thing that would have to happen is that the height cannot continue to increase, right? At some point, the height's going to have to drop down. So let's sort of think about what that might look like. And so I want to think about a function. So I'm going from some value, and we'll still start at 0 for some reason and go to infinity. So I want to think about some function here who, we can let the right-hand bound go to infinity, but then the area underneath this curve will not be infinite. And so let's draw something. And I'm going to make the right-hand side get very low. And so this is our graph for y equals f of x. And so we're starting at 0, and again, we're letting the right-hand bound go out to infinity, whatever that means. And so what's happening? So what could be happening here that would let us have a finite value for this area? So let's think about so this is like maybe 0 to 10. So let's think about this area here, and we'll say, this is some value like 80 or something, or say 73. So let's say that's the area under that curve. And so what happens if we add on a little bit more? So let's say we add on this section more. So let's just go up to like 12 or something. And now this little section here, let's say, is only adding like 1.9. And then let's add another little section here. And so what's the area that we've just added on as we're going out to infinity? Let's say it's 0.09. And then another section, and let's say 0.009. And so on. And so let's say every section we're adding on as we go out further and further is just, it's not getting up to the decimal place of the thing prior to it, but it's just adding on a smaller and smaller decimal as we go out. And so what would this area look like? So it would just be the sum of all these things, so it'd be like 73. So we're just adding all these things up as we go off to infinity. And so what would this be? It'd be like 73 plus this is 74.9. But then the next one has no decimal place, that interacts with these places. So it's just adding another 9 to the end. And then the next one's just adding another 9 to the end. And the next one's just adding another 9 to the end, and so on and so on. And so we would say an area like this, since these areas are getting small enough as we go further and further out, would converge to the number 75. And so it is possible, at least sort of theoretically drawing these pictures, to make these areas as we get further and further out small enough to get a finite area under this curve. And these are things that are utilized a lot in statistics. When you make a continuous distribution in statistics, this is one of the properties you want to have. As you go from negative infinity into infinity, you want it to still have a finite area under the curve because you want that area to represent 100% of the possibility, or usually in statistics we call that 1, right? The probability is 1. Okay, so let's look at the definition of this, and we're going to define this in terms of limits, and we want this definition to give us infinity in a case like this in the first example, and then some finite value in a case like this where this tail, as we get closer and closer to infinity, and the x values get smaller and smaller. Okay, so here's the definition. So we're going to have 3 sort of parts to this definition. So the first one is going to be if we have a fixed lower bound and our upper bound is infinity, and we're taking the integral, definite integral of some function f of x, then the way we're going to do this is actually put a variable in for the upper bound at infinity, and then allow that variable to go to infinity using limits. And so we're going to just treat this like a definite integral. Then once we take the definite integral, then we're going to apply this limit as b goes to infinity. And so remember, in all of these is going to be a fixed constant value for x, and then b is a variable that we're introducing in order to get to the idea of infinity. So another thing that could happen is we could go out to negative infinity and up to some fixed value. And we're going to do the same kind of thing. We're going to take the limit as b goes to negative infinity now, and then b will take the place of negative infinity. A is still our fixed value, which in this case is an upper bound, and the same kind of thing happens. Okay, so there's type 1 and type 2, and then we'll have a third type, and that third type would be, well, what if we wanted to go to infinity in both directions? So negative infinity and positive infinity. And to achieve this, we're going to use the same kind of definition, but we're going to break this up in the middle using a property of integrals we've already seen, which is that I can choose some value in between negative infinity and infinity, which are our bounds, which is every finite number. So not hard to do. Find any number, usually pick one that benefits you. So like 0, c could be 0 or c could be 1, depending on what function you're looking at and what might be easier to compute with. But in the end, it won't matter. So you don't have to be too careful. Okay, so then what happens? Well, then you have two integrals, one going from negative infinity to the finite value c, and one going from c to infinity. And so if we're thinking about what this function looks like, we pick some value c, and if it actually is going to be finite, it'd have to look something like this, and then negative infinity is out here, and positive infinity is out here maybe, and we've just broken it up into two pieces at some value in between. Okay, and so then we're just going to treat each piece of this the way it becomes a type 2 and a type 1 combined, right? And so in the end, we're just going to take the limit as b goes to negative infinity, and then c is some fixed value, and we're going down to b, f of x dx. And then we'll take the limit as b goes to infinity, and this is probably not the best way to do this using the same variable in both places, but just to keep it consistent, do this, and then we'll just compute them both separately, and then whatever answer we get, we'll add them up at the end, and that'll be the answer. Okay, so here are the formulas, and then what we're going to do next is look at an example of each one.